Let's solve problem 6.28 from Microelectronic Circuits 8th edition by Sedra and Smith. There are 4 circuits, and we're assuming that the transistors have very large values of beta, and we need to find the values of the other labeled voltages and currents. So let's start with circuit A. So we can see this is an NPN transistor, so we have emitter and collector and base. So I1, which is really just the emitter current, we can use nodal analysis. So it's going to be 10.7 volts minus 0.7 volts divided by the resistance of 10 kilo ohms, which is a milliamp. Now the collector current, that's equal to alpha times the emitter current. And alpha is equal to beta divided by beta plus 1. But since beta is very large, if we said like this is infinity divided by infinity plus 1, that would just be infinity divided by infinity, which would be 1. So I'm showing that to demonstrate that IC is really just equal to IE, which is 1 milliamp. We can use that to solve for V2 if we travel up from the negative voltage. It would be negative 10.7 volts plus IC times 10 kilo ohms, which is equal to negative 10.7 volts plus 1 milliamp times 10 kilo ohms, which is equal to negative 0.7 volts. So that is the answers for circuit A. Let's move on to circuit B. Okay, let's do circuit B. So we have an NPN transistor again. So we have the emitter at the top, base in the middle, the collector at the bottom. You can notice that because VC, this collector voltage is negative 4 volts, and the base voltage is negative 2.7 volts, the transistor should be operating in active mode because the CVJ is forward biased and the EBJ is reverse biased. I just want to point that out. So let's calculate the collector current first. So that's going to be negative 4 minus negative 10 divided by 2.4 kilo ohms. That's equal to 2.5 milliamps. Now we know that the emitter current is equal to the collector current divided by alpha, but as discussed in the first circuit, alpha is equal to 1 when beta is really, really big. So therefore, the emitter current is just equal to 2.5 milliamps. And we can use that to calculate V3. So V3 is equal to 12 volts minus the emitter current times the resistance of 5.6 kilo ohms. So V3 is equal to 12 volts minus 2.5 milliamps times 5.6 kilo ohms. And I calculate negative 2 volts right there. Okay, let's continue with circuit C. Okay, let's solve circuit C. So this is still a NPN. We have the emitter, the base, and the collector. But this time we have this extra voltage source at the base. So what's this current IB? Well, we actually don't even need to calculate it. Because when beta is very, very large, then the base current converges to 0 amps. Which means V4 is simply 1 volt minus the base current times 20 kilo ohms. The base current is 0, so it just becomes 1 volt. So V4 is just 1 volt. And in order to solve for I5, again we know that IE is equal to IC divided by alpha, but when beta is very large, alpha converges to 1. So we just need to calculate the collector current, which we can do. It will be 0 volts minus a negative 10 volt divided by 10 kilo ohms, which is equal to 1 milliamp. So therefore I5 is equal to 1 milliamp. Alright, let's keep going. Okay, lastly we have circuit D. This time we have a PNP transistor because the arrow is pointing out. So that means we have collector on top, base in the middle, emitter on bottom. Now let's discuss what's going on with the circuit. So the collector and base are connected by this 10 kilo ohm resistor right here. But because beta is assumed to be very high, that means the voltage drop across this resistor will be basically 0 volts because we know that the base current converge to 0. So that means that this base voltage is really just V7. And this also implies that the transistor is operating in active mode. So therefore the emitter voltage would just be equal to the base voltage minus a 0.7 voltage drop. So again, VB is equal to V7, so we can say that the emitter voltage is equal to V7 minus 0.7 volts. What we're going to do is set up some equations to solve for I6 and V7. So we know that I6 is equal to the emitter current, and again, because beta is very high, this is also equal to the collector current. So if we do this collector current, that would mean that I6 is equal to 5 volts minus V7 divided by 9.1 kilo ohms. And then if we take a look at this down here, this bottom wire, we can also say that I6 can be written as V7 minus 0.7 minus the bottom terminal voltage of negative 5 volts divided by the resistance, 3 kilo ohms, because V7 minus 0.7 represents the base voltage because of this drop here. So I6 is equal to 5 minus V7 divided by 9.1 kilo ohms, which is also equal to V7 plus 4.3 volts divided by 3 kilo ohms. So now we have two expressions for V7. So we can solve for V7. Let's multiply both sides by their denominators. So we get 15 minus 3 V7 is equal to 9.1 V7 plus 4.3 times 9.1. Let me look up what that is. That was 39.13. 39.13. Okay, now I'll just solve for V7. So 15 minus 39.13 is negative 24.13, and that's going to be equal to 9.1 plus 3 is 12.1 V3. So V3 is equal to negative 24.13 divided by 12.1. That is equal to negative 2 volts. So V7, I don't know why I started writing V3. V7 is equal to negative 2 volts. And now we can just solve for I6 equal to 5 minus negative 2, so plus 2 divided by 9.1 kilo ohms. So I6 is equal to 0.77 milliamps. And that solves the problem. Thank you for watching my video. For any comments, questions, or video suggestions, feel free to reach me in the comments section or by my email. Thank you and have a great day.